Okay, so now we're going to look at the other model where firms set quantities. We're going to look at the Cournot duopoly model, where both firms set quantities, but they choose their quantities simultaneously so that neither firm actually gets to observe exactly how many the other firm decided to produce before it decides how much it produces. And then after they both decide how much to produce, they're both going to sell their quantities in the same market. So they're both going to sell their identical products in the same market in the same period. Okay, so let's think about this. Okay. They're going to choose their quantities at the same time without observing how much the other produces. Now, we might think that they have a pretty good guess at how much the other one might produce. Okay, but if the other firm were to deviate from their expectations, let's say firm one has some expectation for how much firm two is going to produce. If firm two deviates from firm one's expectation of how much firm two is going to produce, firm one does not recognize that. And so that would not influence their decision. Okay? So both of them are sort of making output decisions based on how much they think the other firm is going to produce. So you might think, how are we going to solve this problem? Well, we're going to assume that over time, they would update their beliefs to be correct. Okay? So the sort of over time, they get an idea of how the other firm is going to produce, and over time, they sort of both eventually end up with the optimal strategy. And by optimal strategy, I mean that firm one is producing a quantity that maximizes its profits, given how much it correctly believes that firm two is going to produce. And firm two is going to produce an amount that maximizes its profits given its correct beliefs about how much firm one is going to produce. And that is, we're looking for a Nash equilibrium where each firm is maximizing its profits given its correct beliefs about how the other firm is going to behave. We can look for a Nash equilibrium graphically. Okay, normally when we plot things, there's some variable that our function depends on, and that's usually put on the horizontal axis. And there's another variable that is the output of the function, and that usually goes on the vertical axis. Okay, so if we were just to plot firm one's reaction function, we'd want to put the amount that it produces on the vertical axis. If we were just looking at firm two's reaction function, we would want to have the amount that it produces on the vertical axis. Now, obviously, we can't have Q1 and Q2 on the vertical axis at the same time. Okay, so we're going to have to bend convention. The dependent variable for one of the two reaction functions is going to have to be on the horizontal axis. So the way I've plotted it here is the reaction function for firm two follows a normal convention, right? So you might take an amount produced by firm one, that's the input to firm two's reaction function. You could trace that up to firm two's reaction function, and the height of that point, that is sort of the value on the vertical axis, would give you how much firm two would produce in response. Now, for firm one's reaction function, we're actually going to have to bend convention. The input variable in firm one's reaction function is the amount produced by firm two, which is shown on the vertical axis. Right? So we might say, let's suppose that this is the amount produced by firm two. To see how firm one would want to respond, we could trace that over to firm one's reaction function. Now, it's the horizontal distance on firm one's reaction function that tells us how much firm one would want to produce. Right? Okay, so let's now think about how we would find a Nash equilibrium. Let's choose this point right here. If you can, oops. The question is that a Nash equilibrium? Well, if it falls on firm one's reaction function, then firm one would not want to unilaterally change how much it produces, right? So we could see, take this point here, we could trace out, it's on firm one's reaction function. It's happy with how much it produces. So half of what we need is there for it to be a Nash equilibrium, right? If this is the amount, if firm one wanted to produce 6 units, to figure out how much firm two would want to produce in response, we'd have to trace that up to firm two's reaction function. Okay, so firm two would want to unilaterally change how much it produces in that case. So it can't possibly be a Nash equilibrium. So what do we need for a Nash equilibrium? Well, we need a point that falls on both firms' reaction functions. So each firm is happy producing the amount that it's producing given the amount produced by the other firm. And you can see that the only place that this occurs is at this point on the graph where the two reaction functions cross. Okay, so that is the Nash equilibrium that we're looking for. We're going to try to solve for both firms' reaction functions, and then we're going to find the quantities produced by each firm such that both of those reaction functions are satisfied. So let's start with firm 1. And the first thing we're going to do is we're going to write down its profit function. So the profits for firm 1 is equal to the quantity that it produces times the price, which we're going to continue assuming the same setup as the last problem, which means that the price via the inverse demand curve is equal to 30 minus the total quantity produced, where the total quantity produced is equal to the sum of the amounts produced by the two firms in this market. Okay. Again, there's no cost function in this simplified example, so we don't need to subtract off the cost to get the profits in this example, although in other examples we would. Now, once we have the profit function written down, what we do to get firm 1's reaction functions is we're going to take the derivative. And since we're maximizing firm 1's profits, we take the derivative with respect to its decision variable, how much it produces. And we're going to set that equal to 0. So let's take the derivative of profits for firm 1 with respect to the quantity that it produces. And that's the derivative is going to be equal to 30 minus 2q1 minus q, oh, that should be 2q1, sorry about that, minus 2q1 minus q2. And again, when we're solving these problems, we always set the derivative equal to 0. So what variable are we solving for? Well, we're trying to figure out what firm 1 will do, right? We wrote down its profit function. We took the derivative with respect to q1. So we're going to solve for q1 as well. And if I skip a couple steps, what we get is that q1 is equal to 15 minus 1/2 times q2. Okay? So this is firm 1's reaction function. So we're halfway there. Now what we have to do next is we have to find the other firm's reaction function. We were first going to write down the profit function in order to get their reaction function. So the profit function for firm 2 is equal to the quantity that that firm produces times the price, which we know from the inverse demand curve is equal to the sum of the amounts produced by the two firms. So if we plug that in, and we're going to go through the same steps. So to get firm 2's reaction function, we're going to take the derivative of its profits with respect to the quantity that it decides to produce. And that's going to give us 30 minus q1 minus 2 times q2. And as always, we set the derivative equal to 0 to find where the function is maximized. And if we then solve for q2, because we're looking at firm 2's decision, we get that q2 is equal to 15 minus 1/2 times q1. So now we have both firms' reaction functions. We have firm 1's reaction function, and we have firm 2's reaction function. Now you'll notice that these two reaction functions are mirror images of each other. And this happens because this is a symmetric problem. Okay? Both firms produce identical products. They both have the same cost function. So now we have the two reaction functions. We want to find the set of quantities of Q1 and Q2 that satisfy firm 1's reaction function, and at the same time solve the other firm's reaction function. That would imply that both quantities are such that each firm is maximizing its profits given its correct beliefs of how much the other firm will produce. Okay, so we have to solve two equations for two unknowns. One way to do that is to plug one of the reaction functions in for the other. So let's plug Q1 into firm 2's reaction function. So that gives us Q2 is equal to 15 minus 1/2 times Q1. But rather than write Q1, we're going to plug in firm 1's reaction function. And after we've done that, we have an equation which only depends on one variable, Q2. So now we can rearrange it to solve for Q2. So that'll take a couple steps. We have Q2 is equal to 15 minus 1, or minus 1/2 times 15, which is just 7.5, minus 1/2 times minus 1/2 times Q2. That becomes plus 1/4 times Q2. Now, if we subtract 1/4 Q2 from both sides and simplify a little bit, we get 3/4 Q2 is equal to 7.5. Say, okay. And if we then multiply both sides by 4/3, we get that Q2 is equal to 10. Okay. So now we know how much firm 2 is going to produce in a Nash equilibrium in a Cournot duopoly. To get how much firm 1 is going to produce, we could plug that into firm 1's reaction function up here, which plugging in Q2 equals 10, we get 15 minus 1/2 times 10, which is just equal to 10. So the solution to this problem, I don't know where that went, is that both firms produce exactly 10 units. Okay, so that we could then go in and we could plug into the inverse demand function to figure out what the price in the market would be. We'd have 30 minus 20, right? Each firm produces 10, so there's 20 produced in total, yielding a price of 10.